When we are solving problem number 4 here. In this problem we have a charge Q that's been distributed in a electroscope. This charge Q has been cut in half, and half of it is on one 2-gram sphere and half of it is on the other sphere. It's equally shared by both sides. We have two 70-centimeter long wires and two 2-gram spheres at the end of the wires, and these wires make a 30-degree angle with the vertical. So what we want to know is how much charge Q was applied in the beginning. The first thing we'll want to do is draw out our forces. So for one of these spheres at the end of the wire, we're going to have the first most obvious force is gravity, which we can label Fg, G standing for gravity. The next one that we have will be due to tension, which is directed back along this wire right here. So we'll just draw a little arrowhead there and call that Ft for F tension. The last one, of course, will be the electrostatic repulsion, and for the left sphere it'll be directed to the left, so we'll call that Fe. Typically, the first easiest one, gravity, that we mentioned, is pretty simple to calculate, so let's do that and see what it tells us. As you'll remember from mechanics, the force of gravity is equal to the mass times the gravitational constant. In this case, we're going to put in 2 grams and 9.8 meters per second. Multiplying those two together, we get 0.0196 newtons. This is directed downwards. The other two forces now that we don't know yet are the electrostatic repulsion and the force of tension. The force of tension will be the simplest one to get next before the force of electrostatic repulsion. That's because if you look carefully at our diagram, the tension force has the gravitational force as a vertical component. Let me show you what I mean. Let's say tension is directed roughly to the upper right. We have gravity going directly down, and we have this angle of 30 degrees. If someone turned this video on at this moment right here, they would think they're maybe in geometry class, because we have this piece right here, which represents the piece adjacent to 30 degrees, and we have this unknown over here, which represents our hypotenuse. So if we have 0.0196 for our adjacent, and we're looking for our hypotenuse, which trigonometric identity do you think we'll be using? Well, if you recall from your geometry class that cosine theta equals adjacent over hypotenuse, you can solve for hypotenuse, which will be our tension force, which will equal adjacent, which is 0.0196, divided by cosine of 30. This should give you 0.0226 newtons. Now we know two forces, and we should probably be able to find the third one. I'll show you how. Going back to our diagram, we have our one charged sphere connected to a rope. We know that this one force is 0.0196, and we found that this other one over here is 0.0226. Yet again, we've made another triangle. So using the Pythagorean theorem, a squared plus b squared equals c squared, we can find what the force along the bottom is, right here. Recall that the reason that these vectors make a triangle is because this ball is in static equilibrium, meaning all the vectors, when added together, balance out to 0. Using that, we find that the electrostatic force should be equal to 0.0113 newtons. You might think the problem is over, but recall that we are calculating Q. The way that we find Q for electrostatic attraction or repulsion is by using Coulomb's law. So this should equal K times Q1 times Q2 divided by the distance between them squared. Q1 and Q2 represent the total bigger charge, let's say capital Q, that was divided in half. So we can modify our equation a little bit and say that this now equals K times Q, the initial charge, divided by 2, multiplied by Q divided by 2 divided by R squared. Simplifying, this will give us K Q squared divided by 4R squared. K is a constant. You can find it in Giancoli. It's 9 times 10 to the 9. And if you look back at the diagram that's drawn on your homework, you can see that we have an equilateral triangle. So R will equal 70 centimeters or 0.7 meters. Plugging all these numbers in, we should end up with a charge of 1.57 microcoulombs. If you have any questions about this, feel free to ask.